That's right. Concentration gradients. Huh? It's just wherever you have a high concentration on one side. Yeah.
And so, will it gradually change and count as high to low?
Yes, that's right. And low on the other. Wow. All right. So you guys do listen. Oh, I can't believe it. Sometimes I don't think you listen. All right. Low on the other.
I just heard concentration because that's the first thing I thought of.
So high to low is fine, but you're right. And the key is that it's going to constantly change, where it goes highest here, the darkest, and it's going to get lightest and lighter and lighter and lighter and lighter till you're the lowest on the other end. So, man, when you guys show me you're listening, I feel like crying. All right, huh? It does. It does. It really does. I hate to say it. It's sad and embarrassing, but.
Me too. I didn't think I was, to be honest. I was like,
Well, at least it shows you're listening, so that's good. So a concentration gradient is this idea that you go from high on one side where there's a lot of it to low, and it has every example that I've given you is I think they're decent examples. The fart's just a funny one, but all of them, the hound dog, all these are examples that I hope will help you remember that a concentration gradient isn't just high on one side, low on the other. There's high and then lower and lower and lower and lower and lower until you're lowest on the other end. All right, so then the other thing was I drew this out here and had put a cell at 10%, and then outside is 20%. And I asked you, oh, that's not right. Sorry. Here is 20%. So, well, hold on. Let's think about it. Now, this is where it gets confusing. This is where everybody gets it. This is where anybody that has trouble is going to have trouble here, okay? In this kind of milieu, all right? So let's talk about this. Obviously, we have a high on this side, right? The outside is high. So the solution, we call this the solution. Everybody agrees the solution is high.
yes.
That's not a problem for anybody. In general, I've seen from your answers and from 20 years of doing this, nobody has a problem seeing that's high and this is low. All right, so that's not a problem for anybody. Well, for most puppies. Let me just ask this question just to round it off. Everybody sees that the solution is high and the cell is low? Yeah. Everybody sees that? Mm-hmm. It's not a problem? Any questions about that? No. All right. So that cell is high, low, and the solution is high. So what do you call the solution that the cell is in? Hypertonic. That's right. This is hypertonic. Let me put it red for hypertonic. This is like heavenly after 2 cups of coffee and a donut. Hypertonic, right? Hyper, high, right? And inside the cell is what then? Hypotonic. That's like heavenly today. And she hasn't had her 2 coffees or her donut.
She did. No, she's saying he's saying if she didn't.
Oh, no, she didn't. She said she didn't. Did you?
I said I did. I just said I was tired.
Oh, so you had it, but you're tired. Are you still? You're still hypotonic, right? But you're not hypotonic. You're just hypo, energy-wise, right? Hypo means low, and hyper means high. So they're relative definitions. You got to get that in your head, right? This is high in relative to this. This is low relative to this. Hypo, what? What does tonic mean? What does tonic mean? I think on the quiz I labeled it with one more clue. 10% solute. And this was 20% solute. What does tonic mean?
Solute.
Solute. All right. So this, when you're talking about hypotonic or hypertonic, you're talking about the solute concentration. What's the other stuff that's in there? There's the solute, and then there's the what? There's two things we talked about over and over again. Solvent, that's right. So there's only two things, either solute or solvent. So let's go ahead and make a pie graph. You remember what pie graphs look like. And if it's 10% solute, if we're talking about 10% solute, I don't know if this looks like 10% or not. I'm just going to go ahead and assume it is. If it's 10% solute, what's the rest of it? 90% what? Bless you. Solvent. What's the solvent in biological solutions in biology? What's most of the time? What's the solvent? Water. That's right. So we're talking about water. So water is very important, and one of the main reasons it's so important is that it's the solvent in most cases, right? So water is a solvent. So water's a solvent, and then this is going to be whatever the solute is. All right, so water's a solvent. And so if it's 10% solute, what's the solvent? It's 90% water. Right? I mean, does that make sense?
Yeah.
Every time you see a solution, if somebody tells you it's 90% solute, or in the case of this example, 20% solute, right? If they tell you it's 20% solute, what is the percent water?
80%.
It's 80% water. So if this is 20% solute, then that's 80% water. So I can say 80% water. And that's 90% water. Now, you have to keep that in mind because later you'll be asked to do things like calculate water potential, and if you don't consider that whatever is left is the solvent, then you're going to run into problems. So in a hypertonic solution, the solute's higher, but the water's lower. Does that make sense? Now, let me be very clear. I'm going to put up two different situations. One where the solute can pass through the membrane. So if the solute can pass, then life's easy for you. If you have a beaker and you have water and you have a cell and you have 10% inside and 20% outside, then what's going to happen if the solute can pass? That's yes. What's going to happen?
Wouldn't the concentration change?
Yeah, the concentration of solute would change, and the solute's going to go from high to low. So that's easy. It's going to go in high to low until it reaches dynamic equilibrium, and what you'll get is something in between 10 and 5. I mean, it's 10 and 20, and it'll be something like, I don't know, I'll just make up a number and say it's 15 on both sides. Till they're equal. And remember, it's dynamic equilibrium. So they're going to keep moving back and forth, but they're going to be equal. They're going to say about 15% on both sides. That's easy, right? Mm-hmm. That's always going to be easy. When you see simple diffusion, it's called simple diffusion. That's right. The other stuff is harder. There's nothing hard about this as long as you have your definition straight. Life is really, really simple. The worst kinds of problems are probably the osmotic pressure calculations, but really They're not that difficult. We're not doing them because I feel like your algebra skills probably aren't up to looking at a bunch of Greek letters on the screen and trying to apply them to osmotic, but I will give you as bonus questions on it. It's you have to calculate osmotic pressure on both sides of the membrane, and then you have to decide which one's more negative, and whichever one's more negative, that's the one with the lower water potential, so the water's going to go into that direction. But that's neither here nor there. That'll be a bonus question. If anyone wants it, they can get that information, and it's very interesting. If you, again, when you talk about blood pressure, right? When you talk about water moving up a tree. When you're talking about why is there swelling during my period, when you talk about why does steroids help with reducing swelling, when you talk about why does my arm get swollen when I get punched, these are all consequences of this water moving, this osmotic pressure difference, and it's really not that hard, but it does require a little more math, so we're not going to go into it. So that's simple diffusion. That's when those kinds of problems, you're like, yes, I got this. Don't make a mistake. It's just high to low. They're not going to tell you it's simple diffusion. They're going to give you a situation. How do you know it's simple diffusion? There's two things here, all right? There's two key points. The first key point is the solute can pass. It can pass. We call it permeability. Permeability. And so the membrane is permeable. They will tell you somehow in the problem. Often they try to throw tricks at you. They won't tell you the membrane's permeable. They'll say, oh, the cell membrane is a cell that takes in sodium in a passive way. They'll phrase it in a way that is going to test your understanding without telling you that it's permeable. Sometimes they just tell you it's permeable. Sometimes they say it does pass. So then you got a bonus because it's easy. The second thing is there's a concentration gradient. And that equals simple diffusion, and that is really a bonus because then it's just high moves to low. The high solute moves to low solute. All right, so that's easy. So those are three-step problem, no big deal. Is it permeable? Yes. Okay, great. If the answer is no, though, that's when things get a little more complicated. I don't think it's that bad, but if the solute cannot move, and I'm going to go ahead and say, let me just say no, right? Move across the membrane. So it's not permeable, right? Then you have the same problem. If I give you the same, and this is where it gets tricky, right? And this side's 20. Now I gave you simple diffusion today. If I have the same problem, the solute can't move. This can't move from high to low because it's not permeable. No, can't move. So what's going to happen?
What did you say? If you can't move?
The solute will not move, but the concentrations will become equal. That there is no question about it. What's going to move if the solute can't move? Solvent. That's the answers to 2 and 3 on the quiz. So if the solute can't move, then the solvent will, the water will. In what direction? Towards into the cell?
Out of the cell.
Out of the cell. Why out of the cell? You're right. It is out of the cell.
10% that's the solute. So if it's the solvent is on the outside, so everything moves towards the outside.
That's exactly, you got it. You got it. There's two ways to think about this. There's more than two ways, but two basic ways to think about this. You can think about it two ways. I don't care which way you think about it. All right? There's actually three ways. I'm going to give you all three ways and then that I can think of right now. I don't care how you think. Whichever one of these three makes sense to you, use that one because they all work. They'll get you the right answer almost every time. So if the solute can't move across the membrane, then the easiest way, this is what I think is the easiest, though I think it's the laziest way, but it is the easiest way. Water will move toward the hypertonic side. All right, that's the easiest way to remember that. If the solute can't move, it's going to move towards the higher solute concentration, wherever it's hypertonic, period. That's all there is to it. Then it's kind of easy. So then the second way, which I think is a little better, a little deeper understanding, is, well, I don't know if it's better, but it's certainly deeper understanding. Water, if the solute cannot move, so water will move in the opposite direction that the solute would have moved if it could. I think it's that's, even though this is more complicated, I don't think it's the best one. It's a more complicated definition. You have to think more about, like, okay, solute can't move, so would and went in, so then water moves out, so because it's opposite. Okay, fine. The best answer in both understanding and to me, it makes sense, but you'd have to understand this, right? You have to understand that water, you'd have to understand that if water is 90, if solute's 10%, water's 90%, and if solute is 20%, then water's 80%. You'd have to understand that to answer it this way. And that answer is water, if the solute can't move, again, let me start with that part of the sentence, because if the solute cannot move, then water will move toward or down its concentration gradient from its high to its low. Now here you have to think about that we're talking about water. When I say it, from water's high to water's low. So we just heard a minute ago one of your colleagues say, if the water is higher inside and lower outside, the water's going to come out. Well, does that make sense? That the water, but in order to answer that, using this definition, you'd have to know that water is lower inside or higher inside and lower outside. How would you know that? You'd have to understand that if the solute's higher, there's only two things in the water, the solute and the solvent. That's it, water and the solute. That's what we're talking about here. And 10% is the solute, then 90% is the water. If 20% is the solute outside, then 80% is the water. So high, low, water moves. This is not simple diffusion. It is diffusion, though. It is diffusion because there's still no active transport. So this is called osmosis. Osmosis. It's the diffusion of water. And this was in your Nearpod. It was in, we talked about it in class a little bit. You saw little pictures of the baggies. And what these ladies over here are going to do for you is they're going to create an agarose gel. They're going to mix a gel. They saw me do it for their class. They're going to make you a gel, and we're going to look at osmosis in a cell. You're going to actually measure it happen. So actually kind of cool. You can ask them. It turned out really well for them. All right. Everybody understand that so far? We're good? So that's all passive. All this is, by the way, is passive transport. And I know we went over it yet on Friday, but I want to remind you one more time. There's a third way of passive transport. This is all passive. You can, when I post all this, you can look at it. But this is simple diffusion. That's passive. What does passive mean again? No energy is being used, right? So no extra energy is being used. And then the last passive one is this thing called facilitated diffusion. And there's only one simple reason why facilitated diffusion could be a problem for you on a test. And I think the AP kids are running into some of this now. Because this is the kind of question the AP exam loves to give. So facilitated diffusion means you need something to facilitate, right? So you're going to need some kind of protein. That's usually your facilitators to cross the membrane. To cross the membrane, you need help. So there's several ways that help can come. And they come in these forms called proteins. Was that in the Nearpod? Yeah, that's excellent. Because this is so this protein allows things to go from high to low. So you go from high to low. So then osmosis doesn't need to happen because you're getting this movement of solutes from high to low through the channels. We call these channel proteins. There's other kinds. There's voltage-gated channels. There's all kinds of different proteins we're not going to get into right at this stage. But just to let you know that what they love to do, especially the AP College Board, but I've seen it on some practice questions, if you change how many of these proteins you have in the membrane, you change how permeable the membrane is. That's why the cell uses this. Like some cells, they let a lot of salt in and other cells keep salt out. How can cells make that decision? How does a cell make a decision on whether to have? How does one cell allow salt through? Na plus does get through. Yes, is the answer to one cell, and another cell says no. And it's the same person, same tissue. Maybe not same tissue, but same organism. What does one cell have that the other
I
doesn't?
can't remember what it's called, but it allows it to, like, the shape to change for it to allow some in and out.
All right, so conformational change. Okay, good. Maybe the protein does a conformational change. That's a really good idea. There's another way, and that's that you can make proteins. One cell could have the proteins in the membrane, and the other cell doesn't. So now sodium gets in this cell, but it doesn't get in the other. Why? Because this turned on the genes for this protein. Because remember, in order to get a protein, you got to go from gene to mRNA. You haven't learned this yet, but you have to go to mRNA, then to protein. Well, this cell has the channel protein on, is on, and what about this cell?
It has it all.
Then this cell, it's off. That's it. You think, well, that's how often does that happen? That you have different proteins in the membrane all the time. That's how you regulate your body. That's how you make decisions, and your body's making these decisions all the time. Heavenly, do you mind if I keep using you as an example? All right, so Heavenly is a perfect example. Oh, I said I'm sorry, it's heaven. I got heavenly. I got 2 heavens and 2 heavenlies, and I got a.
Heaven.
It's heaven.
No, she did. No, she said. That's a new one. I've never heard of heaven.
Heaven. I have 2 heavens and you've never heard of heaven? I've had unique.
I've heard of heaven and unique, but I had heavenly.
I have heavenly. I have heavenly. Anyways, I've heard a lot of different names, and they're all beautiful. But I just tell you that it's hard to keep track of all of them. But let's take a look. Let's look at Miss Fudge's example. All right. What?
I'm talking about them.
Oh, okay. All right, so let's look at an example. So Miss Fudge gets up in the morning. She's tired. She has breakfast. She has her routine Monday morning breakfast, 2 donuts and 2 coffees. Is that right? Or is it 1 donut and a coffee? It can, whatever. So what does that do? That takes, remember we drew a blood vessel. So in her blood, now she has a lot of sugar. That's not good. Because that sugar is a solute. What would happen if Miss Fudge's body didn't do something when she got all that sugar in her blood? What would happen to her blood? What would happen? The cells, remember these are cells, her blood vessels are made of cells. What would happen if there's a lot of solute in her blood? Her vessels would, good. Excellent. Water would rush in. Water would rush in into her blood, and it would start to swell. What would that mean? Increase in what? Close, not blood flow, blood pressure. And high blood pressure is dangerous. We all know that. So anyone who you know is diabetic, I'm diabetic myself, anybody who knows diabetic has to be careful with this, because as the sugar flows in, then water starts to flow in because sugar can't move. Sugar can't move into the cells because it's big and polar. It needs a facilitator. It needs a helper. And diabetics don't have that helper easily available to them. Is that clear?
Yes.
So we call that an increase in blood pressure. Could cause embolisms. It can cause nerve damage. It can cause blindness, circulatory problems. All kinds of things happen. So it's really, really bad. So Miss Fudge's body doesn't want that to happen, right?
Correct.
So she eats that sugar. What is Miss Fudge's body going to do? She's going to start making this protein called insulin. You've heard of insulin.
Yeah.
So insulin is a very interesting protein. And we're going to use this to explain to you. We're going to use a few of these things that we've talked about. So here's Miss Fudge's cells, and just inside all the cells of her body except her brain. By the way, I'm saying Miss Fudge, but I'm talking about you as well. Not me though, but in her cells, a bunch of vesicles sit in the membrane inside the cytoplasm, and they hold this molecule called insulin. Not insulin. This molecule called glucose. Let's just call them glucose channels. They have an actual name. I can't remember them right now, but they have these glucose channels sitting in these vesicles, and these vesicles all tied down like a hot air balloon roped down to the ground. Have you seen those before? Mm-hmm. you don't want to let the hot air balloon go because it'll start flying away. But they have all these channels that are gonna, these channel vesicles that are holding the channels ready to go. If the cell gets a signal, it's going to release these vesicles. They're going to fuse to the membrane. And then what are you going to do? What's going to happen to the membrane if that happens? What happens if the cell receives that signal and then gets, and these vesicles that have these channels fuse to this membrane? What happens to that membrane?
It's going to open?
Well, it's not, in a way. What's going to happen is if it receives a signal, then it's going to release those vesicles, and then in the membrane, you're going to have the channels. Does that make sense? So now the membrane has the channels. Before, it couldn't let sugar in. Sugar couldn't get in. So blood pressure went high because water rushed into the blood vessels, and all kinds of problems happened. And heaven's body started, God forbid, starts to release, starts to have nerve damage and circulatory issues, and etc. So we don't want that to happen. So your body sends out a signal. What's that signal? It's insulin. And insulin's released by her pancreas, this little weird looking thing called the pancreas. And it has a bunch of these little cells in it that produces insulin, and that puts that into the blood. As soon as her pancreas says, oh, sugar, her body starts to put insulin into the blood. And when the insulin gets in the blood, it goes and binds to signal receptors on all her cells except her brain cells. Her brain cells always take in sugar. They don't need an insulin. All the other cells need to have these receptors that signal the cell, hey, release the vesicles. Release the vesicles. Let the glucose channels in the membrane. And then what happens when the glucose channels come in? Do we get osmosis? Is osmosis happening if glucose can get in? See, before glucose, the solute, glucose, could not get in before the signal. So what would happen when you eat sugar? You're going to get osmosis, right? And the water is going to go flowing into the blood. That's not good. But if the glucose is not in the blood, what happens if all the cells of your body get this insulin signal, they release these channels, will there be osmosis? No, why not? Why won't there be osmosis? What's going to happen instead? Well, what's going to happen instead is glucose is going to move in. Because if the solute can move, what will happen? If the solute can move, what will happen? What is the process that we call simple diffusion? If the solute can move, then we'll get simple diffusion. And what will happen is these glucose molecules, because you have these channels, will go right into the cell. And your cells start to, all of the cells of your body. And so what happens, you have less sugar in your blood because now all the sugar's in the cells. And your body starts breaking them down. Either turns them into fat or turns them into energy, whatever it is, so that you can be awake and pay attention in class. Your blood cells are taking apart that sugar and getting ATP. Your brain cells are like, all right, now I'm awake, right? But without that sugar, without that insulin, the sugar stays in the blood. Your cells never get the sugar. So you're still tired. You have high blood, so become tired. You have high blood pressure, and all kinds of other bad things happen. So insulin is really important. Well, I'm going to do a graph now. I know you don't like graphs, but I'm going to go ahead and do a graph. So what happens is, this is Fudge's, how do you spell your last name? F-U-D-G? D-G-E. So Fudge's blood, and is the name of the graph. And when we look at concentration of blood sugar, BS, over time, she eats, and as soon as she eats, the concentration goes up. Then the concentration starts to come down. This is normal. This is normal. This is what she wants. She wants to keep it normal, but this is too high. What happened at this point? It was her blood pressure was getting a little high. She had a lot of sugar in her blood. Well, what happened? What did she do for it to come down? What did she do? Her blood sugar to come down. Her pancreas did what? Released insulin. So she released insulin. And now her body let the sugar into the cells. All right, that's fine. Blood's coming down. But what is it down here?
It's too low.
It's too low. That's not good. So her pancreas released another hormone. These are called hormones, by the way, these signal molecules. They have another receptor. All her cells have another receptor. They released another signal called glucagon. You should know both for your test. Glucagon is just another name for another. It's the partner to insulin. You probably never heard of it, but it's its partner. So the pancreas releases glucagon, and what that does is shut down the channels, and up goes the sugar. Because now you stop taking sugar out of the blood, right? It also tells your liver release sugar. Your liver releases sugar as well. So that does more than, all these hormones do more than one signal at a time.
So the glucagon shuts down the channels that the insulin.
That's right, and it just keeps doing this all day long.
So what happened if your pancreas you don't get any insulin?
Then you're what we call a diabetic. If you're not getting any insulin at all, you're type 1 diabetic. Most of type 1 diabetics are born that way. If you're resistant, if you don't have receptors for it, then you're type 2. One last thing before you go. This is staying at equilibrium. This normal is what we call equilibrium. Is it static? Is it not changing? No, it's constantly changing. So what do we call it? Dynamic. So it's dynamic equilibrium. Really, this is all connected. I'm not just every day's lessons connected every other day, guys. Does this all make sense?
Yeah.
All right. I'll post everything. I want to break it up into chunks and then label each one and put it on your Schoology. Does that make sense? All right.
You don't be looking up on so much.
Yeah, that's why I wanted you to do it in your part. So I'm glad you recognize that. All right.